Okay, this hour we'll talk about more about entropy. So the first concept is conditional entropy. So very similar to conditional probability. For conditional entropy, it also evaluates the uncertainty value of a system Y, and under certain observation, which is the big X, which is our feature or the observation. So it's very similar to conditional probability. For the every event of this random variable X, okay, we have several different events and their probability to observe such kind of event, small x. So that is the probability. So here we use the concept of expectation. So it's very similar to conditional probability. So we use this small x and its probability and times its conditional entropy. Right? So under such observation, what is the uncertainty value of this system Y? So we will skip the mathematics thing. So the result is like this. Okay, so that is the concept of conditional probability. And also, mathematicians also tell us that the conditional probability equals to the entropy of X and Y minus the entropy of X. So that is how it is derived. And we can see that the final result is exactly the same, right? It's exactly the same. So this formula sustains. Okay, but in our case, we don't use conditional probability over the probability. Sorry, the conditional entropy or the entropy right here. Rather, we like to introduce another concept called relative entropy, and we will use the relative entropy to help us to find some interesting mathematical or statistical property. Okay, so here is the example right here. Okay, relative entropy is also called KL divergency or called KL distance. Okay, the distance or the relative entropy or the KL divergence, this value is used to measure the distance between two distribution, and we say that is P and Q. Okay, think about one thing. Okay, I here we have a table right here. Okay, right here that is P. P is the usually we say P is the true distribution of something. Okay, the true distribution of something. But as we know, we can only collect some sample data from P, right? But the collection of the sample data might be not that good, or the way you collect data or the way you sample the data or the model you use to describe the data is not that good. So Q is another distribution. Okay, and that maybe that is the distribution of our model output. Okay, so we have several different ways to output I mean to describe the probability P. Okay, here is an example. Okay, we collect n data points, right? And for the true distribution, the value should be 0, 0, 0, 0, 1, 1, 0, 1. But our model or our algorithm, okay, we use algorithm or a model to describe such kind of data, but the output of our model is 0, 0, 0, 0, 1, 1, 0, 1. And you can see that these two distribution is exactly the same, right? So we say the P distribution and the Q1 distribution is the same. So ideally, KL distance between P and Q1 would be 0. That means they're very close. Okay, and here we can see that is another distribution to describe the n data points, but there's something wrong with some samples right here, right? So such kind of model or such kind of distribution Q2 is not that good. So the P and Q2, their KL divergency will be larger because they are not similar, right? So we need some algorithm or we need some mathematic tools to help us to measure what is the difference between two distribution, right? So here is an example. For example, that is the feature, and we have a distribution P and Q right here, and P is the true distribution. So for us, while we making a model, a mathematical model to describe our data, okay, we wish the distribution we have or the model we have should be close to the true distribution. Although we know sometimes our model is not that good enough, so the output of our model would not be the same as the true distribution. So you can think of one thing that the P distribution is the Y value, okay? And Q1 will be the Y hat value, is the output of our model Q1, okay? And that is the Y hat value of Q2. So in this case, we can use KL divergence to help us to find which model is better because their KL divergence distance is smaller, right? Apparently, in this case, Q1 will be the better model, right? But how do we do such kind of how do we calculate such distance? Okay, so here is the definition. The KL divergence of two distribution P and Q. The definition is that is the expectation value of this one. And this looks very familiar, right? Because we can write it in this way. Right? So that means that is the information, right? That is the information. This value, the red one is the information, right? And we say that is the expect value of information, so that is the entropy. But the probability right here is defined as this one. So given X, we put the X into the model and we want to see the output of Q distribution and output of P distribution. And we use this value to as the probability of P and Q. Okay, and so on and so forth. We just simply just do some derivation. Okay, and at the end, okay, we have two different parts. And here we have this one, that is the red part one. And here we have the second red part one. Okay, and we first take a look at the first red part. Okay, and that value is the expect value. So that is the probability of X, right? It times this value. And the red one, okay, sorry, the green one right here is exactly the information of X, right? And here is the probability of event X. And so this blue one will be the entropy of P. But again, usually the entropy is defined as this, right? You should put it in this way. So here is a minus right here. So the red, the blue parts is exactly the entropy value of a system P. And don't forget there's a minus right here. So at the right hand side, you can see that that is the probability of X in system P. But here, okay, here, that is the, so again, we can write it in this way. So again, this one would be it's very similar to entropy, but the probability right here and the probability right here is not the same. But they are also both describe the probability of a certain event X, right? But the probability is right here, the probability is for P distribution, but the probability right here, we use the Q distribution. So that is the expectation of this value. So let's take, again, we can take look at this this one, okay? So that is this one, and that is this one. Again, the final result is right here. It's right here. So in order to measure the distance between two distributions, the final result would be such like this one. And you can see that this part right here, that is this entropy of P distribution. So it really doesn't matter we have this one, right? If the distance is large, and the first part should be large, because every Q distribution, Q1, Q2, Q3, Q whatever, all of them need to deduce this this value. So it really doesn't matter if we like to measure the distance between two distributions, we use this part. It's good enough, right? So the problem becomes that this one. How do we calculate this value? Okay, and here is the answer. Okay, if you take a look at, please take a look at the description right here. But the result is here. Okay, it's like it. Okay. And that is exactly the definition of cross entropy. Okay, so let's take a look at this one. Okay, if this system, I mean this PQ system, okay, it has only two events, either 0 or 1. Okay, either 0 or 1. So let's first look at the X, because X has only two events, right? So basically the sigma right here, we have two different components. The first one is right here, the second one is right here. The first part is X equals 1, and the other part is X equals 0, because we have only two events of X in both P system and Q system. So we can simply just write two parts. Okay, and think about this one, okay, the red one. The probability of X1 in P system, and we define its value as small p. Okay, and here is the probability of event X equals 0 in P system. And we say that in P system, we have only two events. So the rest of the part should be 1 minus P. The probability value should be like this. Right, for the second part, okay? Log 2, we simply just put log 2 right here. And here is the probability of event X equals 1 in Q system, and we define it as Q. And again, we see that right here. That is the probability of X equals 1 in Q system. So the answer equals 0 in Q system. So the result should be 1 minus Q. And here's the log 2. Right. So you simply just derive it. Okay. And we can see that in the two event system, okay, eventually the result looks like this. And think about one thing. If P, okay, P is the probability of, when we say P, okay, it means the true distribution, right? So the probability of P and its value is x1. We can simply just define it as it is the value of P, which is the true distribution, which is y. I think that is good, right? So 1 minus P is 1 minus y. And Q is the model we have. As I mentioned, that is another distribution. Maybe Q is one of the models. right? So probability of Q, that means we can put the feature in our model, that is our model. And it is an unknown function which is called f. It has certain parameters, theta. So if the model is a linear regression, so the f theta should be y equals ax plus 1, ax plus b, something like that, right? So 1 minus q, that is 1 minus f of x. So again, the p right here is the correct answer, is the true answer. The q right here is the output of our model, right? It's the output of our model. It's the output of model. So that is the y hat, right? Because q system is our model. So think about this one. It is this formula, this equation, is exactly what we introduced in logistic regression. And when we talk about logistic regression, right? When we talk about logistic regression, again, we have two values, right? P and Q, for example, y and y hat. So the y is the true value of your classes, win or not win. The Q value or the y hat value is exactly the output value of your, for example, logistic regression, right? So if it is larger than 0.5, so you will write 1. It belongs to class 1. If the y hat value is less than 0.5, and we say the prediction result would be 0, which belongs to class 0. So it's the same, okay? So go back to find the maximum likelihood, okay? So we have the value of likelihood, right? It is we have multiple we have a pi, we have a lot of multiplication right here. So that is the likelihood. So go back to the logistic regression and take a look at the likelihood. We want to maximize the likelihood, right? So it is very difficult to calculate such values. So we say that we can use a minus log or minus log likelihood value. We can minimize this value. So this value is exactly this one. It's the same. So from the perspective of maximum likelihood and the cross entropy, they both tell us how to evaluate two different data, which is y and y hat. They use the same concept, okay? So it is the same. So after that, when we talk about how do we evaluate the logistic regression, we can say that we use the minima minus log likelihood to evaluate two different output of logistic regression and true value. And we can also say that we can use cross entropy because the result will be the same. Okay, so the result will be the same. So here is, so the rest part is that this, the information of this should be likely. That's called information gain. We will talk about information gain by using real cases. Okay, so that is the concept of cross entropy. Okay, it is from relative entropy and conditional entropy. Okay, so the next thing is we should go back to discuss the when we talk about tree algorithms and how do we find the most important feature so that we can divide the entire space into two subspaces, right? But how do we find the very first features? Okay, so here is an example that we have 10 data points right here. So we have 3 different features, and here's the y. Okay, and you can see that for the first feature, okay, it is the singularity. Okay, so that is we have 3 different classes, okay, less than 5 years, between 5 years to 10 years, and larger than 10 years. Okay, we have 3 groups right here. Okay, so the education is either G or C, college or graduate school. Okay, the experience is Y and yes and no. Okay, and the performance right here is also categorical, is either good or okay. So we have a lot of example data right here, and you can see that in these cases the features and the target, they are all categorical data. So for tree algorithms, it really doesn't matter you use numerical data or categorical data, and we will show you how to do that. Okay, so the first thing is that we would like to calculate the information gain. So the very first thing is that we have a system Y right here. We have 10 different values. Okay, they are good and okay. So the first thing is that we don't need to care about features. We only focus on Y. So the system Y, okay? What is the entropy of system Y? So the definition is right here, right? We have 2 different values of Y, which is either good or okay. And we use the probability of different events and its corresponding information value right here. Okay, so since we know Y has only 2 events, so the first event is good, the second event is okay. So here's the probability of good event times, okay, is probability. Okay, don't forget there is a minus right here. So the second event is the probability of okay, right? So that is the information of okay. So simply just calculate value, and the result is 0.1. So that means, so think about the definition of entropy. That means uncertainty, right? The value is between 0 and 1. So 1.0 right here is that this system Y, which is the target, okay, the output value of Y, which is right here, the uncertainty of Y, this Y random variable, is very has high uncertainty. Basically, because you can see that we have 1, 2, 3, 4, 5. We have 5 G and 5 OK. So probability of G and OK are both 1/2. So that is if Y is a random variable, it is very difficult for you to predict what is the next value of Y, because the probability of next event, no matter if it's G or OK, they're both 1/2, 50%. So that's it. So that means Y is very unpredictable. So the entropy of Y is 1.0. So that is the definition. We just calculate this value. Okay, so the information gain is that we can simply select, try to calculate the conditional probability, conditional entropy right here. So let's take the X1 for example. Okay, let's take a look. Under we have the observation of X1, how uncertainty the Y is. That is the definition of entropy. Y conditioned by X. That is the definition of this conditionality. Under X1 observation, how uncertainty the Y system is. Okay, and we can see that X1 had 3 different values, right? 3 different values. So when we calculate the conditional probability right here, okay, we first need to calculate 3 different entropy, which is this one. What is the entropy of Y under condition that X1 less than 5? And that is another event, the second event. Okay, that is the third event of X1. So under 3 different conditions, and we have to calculate their corresponding conditional entropy. So definition is exactly the same. So we need to find out the probability in that table, and so on and so forth, so on and so forth. So after that, the conditional probability of y, the condition entropy of y under x1 less than 5. The value is this one, and the second value is right somewhere there. Okay, so we have 3 different conditional entropy. And what is the value of this one? Because we have 3 different events of x, y, 1, so we simply just use the probability of 3 different events as the weight of their entropies, and we sum of them together. So from the perspective of y, under the condition that we can observe x1, the uncertainty of y is this value. So compare so here. So you can see that we have 2 different values. The first one is the entropy of y without considering any x, and the later one is the conditional entropy of y conditioned by we observed x1. So there's a difference, right? There is a difference. So the entropy decrease if we have observed x1. So after that, we can calculate all those values, right? So if we observed x1, so we can say that the information gain of xy is this value, 2 is this value, x3 is this value. So we can see that if we have x2 right here, and we can see that the whole system, the entropy of the whole system and the entropy of this conditional entropy, it decreased. That means the uncertainty decreased. And for x2, the value of the decrease is the largest among all 3 different conditional entropies. So we can say that x2 brings the most information to this system. So that is the definition of information gain. So from the perspective of information gain, we should choose x2 as our boundary line to divide our space into 2 subspaces, because x2 has most significant information gain among all the events features. So that is how we evaluate which feature should be the first one to be the boundary line. Okay, and we can see that we have, of course, mathematicians has several different methods to tell us how to find such kind of most significant features as the first boundary line. So here we have another definition, which is called Gini. Okay, a definition of Gini of a system is like this one. Okay, you simply just put all the probability of all events. For example, for the Y system, in our cases, Y is either good or okay, right? But the probability of good is 5/10. The good is 10/10. So the Gini value of this Y system, you can calculate in this way. Okay. So that is just another measurement to measure the system. Okay. So again, if you condition by x, so that is the definition. Again, it is very similar to expected value. Okay, under condition. So we have 3 different events of x, right? Less than 5, between 5 and 10, and larger than 10. So again, we have several corresponding probability of those events. So that is the result. And again, the Gini value Okay, so that of y under we observe x, under we observe x2, under we observe x3, it can be calculated by expected value. So here's the probability, and that is the Gini value. That is the probability Gini value, probability Gini value of the of these three, right? So that is the average expected Gini value of y if we observe x1 and so on and so forth. And again, mathematics can tell us choose the delta Gini, okay, and the value should be the which one? That should be the largest one, and choose the largest one. That means your system, the x2 is more valuable when you use Gini value to evaluate system y. So that's just another thing. But you don't really need to remember all this mathematic things, because all the packages will calculate these values for you. So that you can simply use Orange to find out all these values, and it will sort the value, so you can see that which variable is more valuable than the others. So here we have another one. It is from chi distribution. So that is another evaluation. Okay, it's very similar. Okay, we put all the events right here. Okay, so that is y. That is we consider x. We have 3 different x1 events, right? So that is the count in our data set. How many data set is how many good employee are there when x1 is less than 5. So here's the sum value of these two. So the red part is the average value of 5, average value of 3, average value of 2, because we have 2 events. So that is how you calculate the chi value. And again, you choose the largest one. And from the perspective of chi distribution, x2 is the most valuable feature. So of course we have several mathematicians has designed several different method to tell us which variable should be the first boundary line. Okay, so and again we have another things right here, something like I will tell you how to draw a figure. Okay, so here's another example that we have y and x, right? But right here, that is the numerical data. So how did you evaluate which x1 or x2, x3, which one is most significant of y? So so the concept is called variance. Okay, so that's if I have n data point, for example, with n 100 data point, for certain features in this 100 data point, I can calculate the average value and the standard deviation. So we use a variance. Okay, we can use the variance of x1. We can calculate this value. Okay, and how do we divide this 100 data point into 2 smaller data set? We can try. Okay, we can try. Okay, for example, I have 2 different features. Okay, we have a lot of features. Okay, which feature can divide those 100 data point in a more efficient way? So for example, here we have we divide the data set to 40 data points and 60 data point, and then we can calculate the x1 value, the average x1 value, and its variance. For example, the average value of x in this 100 data points is I think I have okay, for example, the average would be 137 and its variance is 45, 54. Okay, if we divide it by x1 and at the left hand side the average will become 50, at the right hand side the x1 average will become 160 and the variance become 24 and the variance of at the right hand side becomes for example 15. And you can see that you divide the entire data set into two different subgroup, right? So they have their own average value and their variance value. So we can calculate that on the average, the variance value of the entire system, if we divide it into two subgroups, the value should be we use a weight expected variance, the concept of expected variance. So we have 40 data points right here, and its variance is 24, and we have 60 data points right here, its variance is 15. And we can expect that this value should be smaller than the original one if you do not divide the original 100 data points to these subgroups. So such kind of division makes sense because the variance becomes smaller. But if you use some other value, for example x2, and you find out that the average, the expected variance value does not decrease or decrease not as much as x1, and in these cases we can compare different features x1, x2, x3, and we can see which features can do the division more reasonable and more efficiently, which means it has a smaller variance, average smaller variance. Okay, so we have an example right here. You can take a look at this example. So we have several different mathematic tools to tell us how to do such kind of decision to find the first boundary line, first feature, to make the first boundary line, right? We have information gain. Okay, it is from the concept of entropy, right? We have Gini value. We have chi value. We can use the variance to do such kind of things. All those algorithms, they simply just achieve one goal. If we divide the data points to two subgroups and the Gini value or the information gain or the entropy or the variance, okay, would become better if we divide them, use x1 or x2 or x3. So we can compare which one would be better. So that is the mathematics behind this decision tree. So let's take a look at Orange. I'd like to show you how to use Orange to perform all those tree-like algorithms. So first, we can get a file. Okay, so you can select Titanic. So we would like to use Titanic right here. Okay, so you can see that the Titanic dataset in Orange is simplified. So it has only three different features, and all of them are categorical features, and one target, which is survived. So it's yes or no. So we can take a look at the data. Okay, so that means we have 2,201 data point, which is the passenger information. Okay, 3 features. They are all categorical features. Okay, and here we have it is the pathogen is either survived or not survived. So as we mentioned before, because it is categorical data, so we can simply use tree-like algorithm, which is right here, to do some test. Okay, so for the test and the score widget, we put data to the test and score, and we ask them to use decision tree to do such kind of classification. Okay, so you can click the configuration of tree. There are several important things you need to know. The first one is binary tree. Okay, as we when we show how to divide the entire plan into 2 subplan, okay, in the very first figure in the tree class node, okay, if we divide a space into 2 subspace, okay, so we have 1 cut and we have 2 spaces, right? But for some algorithm, you can directly cut the space, okay, divide the space into 3 different subspace, or 4, 5, or 6. It really depends on your features. For example, right here, the sex feature has only 2 values, which is either male or female. So you can use male or female to divide the space. But for example, the status feature, okay, we have first class, second class, third class, and the crew. Okay, we have 4 different values in this categorical feature. So you can simply just use this 4 value to divide the space into 4 subspaces. So it means you want to use binary or not use binary. It's depends on you. It really doesn't matter. Okay, so when we divide the space, okay, the second parameter right here is the minimum number of instances in lib. That means in each space, subspace, how many data point, which means instance right here, there should be at the minimum 2 instances in 1 subspace, right? So the number is 2, but you can change it if you want. That means at least for each subspace there should be 2 instances. Because if the value is 1, that means you can 100% classify all the data, because every instance is in 1 single subspace. You can do that, but that doesn't make any sense. So the 2 is a good value. The 5 right here is that do not split subset smaller than 5. So that means if you, for example, originally you have 6 data point in 1 area, and you want to divide this area further into 2 smaller subspaces. If it has 6 data points, if you divide it into 2 subspaces and one has 3 data point, the other has 3 data point, that is okay. That is not okay, because both split data set should have, if you have 6 data point, you can divide them into 3 and 3. That is okay, because the minimum value is the minimum number of instances in the subspace is 2. So 3 is okay. Okay, but if you have a area which has 6 data point, and you further divide it into 2 and 4, that is okay. But after that, you cannot further divide these 2 and 4 space smaller, because it will violate this one and this one. Okay, so that is how many boundary line you can draw, at most 100 levels. Okay, and that is if a class, okay, for example, you have 100 data points in one area, and 95 of them are class 1 and 5 of them are class 2, you cannot further divide this subspace because its majority reaches 95%. So we have several different parameters to, but as I mentioned, usually you don't change these things. So simply just put it into test right here. So I'd like to talk about how did you do test. Most of the time, okay, we have only one data set, which is, for example, we have 22 hundreds and one instance right here. Usually we don't have two separate data sets, so sometimes you don't have testing data set. So here I would like to introduce an important concept which is called cross validation. The 10-fold, that means that you divide the entire 2,200 data point into 10 subset data set. Okay, each subset set has 220 data point, and you use 9 sub data set to train your model. Okay, for linear regression, you find the best A and B. For the logistic regression, you find the best A and B again. For the SVM, you find the best width. For the tree, you find the best boundary line, something like that. And you test the rest of the one sub data set, which is the 10% of data set, as the testing data. Okay, and the 10-fold means you run the test 10 times. For the first time, you use the first sub data set as the testing data and the rest of the 9 as the training data. For the second run, you use the second data set as the testing data and you use the rest of 9 as the training data, and so on and so forth, until you use the 10th sub data set as the testing data and use the first to the 9th sub data set as the training data. So you have 10 rounds to do. And so here we have the average qualification accuracy, or F1 value, precision recall value right here. So that is one of the way, if we don't have testing data, we can use the 10-fold, which is called cross validation, to perform testing. Okay, and again, here I would like to show you, although we told you that SVM and the logistic regression, they are only for numeric features, but there are some ways, but we'll talk about how to do so. There are some other ways to transform the categorical data to numerical data. So you can still use SVM on the logistic regression on categorical features. So here we simply just connect it to the test and score. Again, we can see that here's the result. Okay, for the tree and for the logistic regression, they have a very nice classification accuracy, but for the SVM, it doesn't work. It doesn't work. Okay, and I'd like to show you something that for SVM, okay, you can click it and see the kernel right here. We have told you what is linear kernel, right? And what is polynomial kernel, which is we have a constant C right here and a D degree. And here's the RBF kernel. So you can try linear kernel, polynomial kernel, or RBF kernel, okay, to see if you need to map your low dimensional data to higher dimension to do SVM. Okay, but most of the time you simply just choose RBF, which is the ideally that is the best kernel you can use. Okay, but for this data, it really does not perform good. And again, we talk about the confusion matrix, right? So we have 3 different models and therefore classification, so we can draw the confusion matrix right here. As we have true negative, true positive. We have 3 different feature models. They have different confusion matrix, and we can also draw the ROC curve we have talked about. Okay, and as I mentioned, you can draw a line start from the left up corner. Okay, and it touches to some points, right? That means that is the sweet spot of an algorithm. So for example, for tree algorithm, okay, the sweet spot is right here. That means if you have around 70% of false positive rate, and your true positive rate would be some place like here, for that is maybe 99%. Okay, SVM is right here, so it is a very bad model. Okay, so that is the logistic regression. Okay, so the area under this curve, if the model is good, the area under this curve should be large. So that's how you interpret the ROC curve. Okay, so here is the prediction. Okay, if you would like to take a look at the result of each model, you can simply just do so. Okay, you connect the data to the model, and you use this model to do prediction. So okay, we need another data set. Okay, we need another data set, so we can do this one. Okay, we can use the original data and use a data sampler, so we have 60% of sampling rate, and we use right here 60% of data to do this tree model, and we use the rest of 40% of the data. Okay, for prediction, and then we can so I can delete this one also. That will be, so we have a data sampler here. So at the top link, it has 60% of the data, and the bottom link, it has 40% of data. We use 60% of data to train this model, so it has a tree. And so again, in orange, we have a visualized tree viewer right here. So you can just simply connect the model to the viewer. So here you can see that it is a tree, right? So from the root, okay. So the question is the sex. So left hand side is female, right hand side is male. So for the female part, the second question is status. So the left hand side is third class, and right hand side is not third class. And the next question is the age. So the age is adult, the age is children, and you can see that here is the decision tree. And for some node which performs quite good, for example right here, that means after we divide the subset by using second class and third class, okay? So at the right hand side is the second class. The prediction is quite good because out of 107 data points, 97 passengers, they survived. And they are passengers who is in second class, and who is adult, who is male, something like that. So you can see that the decision tree can help you to define several different rules, okay, to figure out the passenger is survived or not survived. Okay, again, if you do the prediction, okay, you can see that we can see here is the gray column is the actual value of survived. And here we can see that the tree model says no. The prediction of tree model is no. Okay, and the probability of no is 70%, 30%, and so on and so forth, so on and so forth. Okay, so that is the way you use Orange to analyze data. Basically, you don't need to write code. So for me, if I need to run tree algorithm, usually I don't use Python because Python is a little bit it is not that convenient. So using Orange is much better. So so that is how you do such kind of analysis. And again, you can use as many models as possible in your workflow. Okay, so we could compare the performance of different models. Okay, so that is trees algorithm. Okay.